This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. Today we're doing the ever-popular Cosmic Queries edition. Chuck, good to have you, man.
Always a pleasure to be here.
You're preloaded with Cosmic Queries from our Patreon members. And let me remind you that it's Patreon members and only Patreon members who ask questions. So what's the topic today?
We have cosmological
Oh,
curiosities, which
cool. Cool.
that
Cosmology.
covers enough of it.
You got you. I got you. And if something I don't know, I have to call my people. I got cosmology friends. Just to be clear, it's not cosmetology. That would be makeup and other.
Yes. Now that would be interesting.
So what do you
All
have?
right, let's jump into it with Danny K. Danny K
Is he from
says
somewhere?
he's nope.
Okay.
No, he's
Danny
just
K
Danny.
from the ether.
He's just Danny K from the ether. He goes,
Yeah.
"Good morning, gentlemen of the court of knowledge and His Majesty Neil deGrasse Tyson." I,
Like, dude,
Danny.
we're going to answer your question anyway. You didn't have to. This is,
Yes.
even though you are asking that question first. I don't know what.
And actually, he does put in here, he goes, "I am hailing from the Netherlands, Rotterdam. Come to thee and these humble inquiries of knowledge." Okay.
Nederlands. Okay. So what does he have?
There he goes. He goes, "In a previous episode, there was a mention of an expanding of our universe and that there could be a point in the distant future where we would be stretched to a point where our neighboring galaxies would be too far to reach. Would this expansion also affect our solar system as well? Does it mean that our blue ball would slowly drift away from our star? And would our star dim before that time comes? And if so, would you suggest how we might be able to survive something like this?"
We're all going to die. No.
Very simple, Danny.
Yeah, so in the vacuum of space, there's this mysterious pressure forcing an acceleration of the expanding universe. We have a word for it, but we don't know what it is. We had no business naming it, really. And it's called dark energy. And I joked that we should just, dark matter, we don't know what that is either. We should just call it Fred and Wilma, just two words that don't hint at anything physical, right? Because we don't really know what's causing it, but we can measure it. And so this expansion of the universe that's accelerating, that will continue to grow. And the bigger the universe is, the more vacuum there is, and this pressure is a property of the vacuum. So, as the universe expands, the gravity gets thinner. What we call the gravity density gets thinner, but the dark energy continues to grow relative to the gravity. So initially, all the galaxies will expand beyond our horizon, and then after that, it will start ripping apart the galaxies themselves,
Ooh.
because that's a stronger gravitational force holding them together. Start ripping that apart. And so the solar systems will be flung hither and yon. Then it'll start ripping the planets out of their solar systems. Then it'll start ripping moons from their host planets. Then it'll start ripping planets apart structurally. Then it'll start ripping apart the molecules. Then it'll start ripping apart the atoms in the molecules. Then it'll rip apart the nuclei of the atoms. Then it'll reach the point where the very pixels that comprise the fabric of the universe will succumb to this ripping force. And it's called the Big Rip because we do not know what will happen after that moment. At that moment, the universe will tear because it will no longer be able to stretch in response to that force. We call it the Big Rip, and it will happen if nothing else is in the way. It's going to happen in 22 billion years.
Well, there you go, Timmy. Good night, and you sleep well.
Hey, have a nice day. Have a nice day, Timmy. So yeah, the sun will be long dead by then. Sun will give up the ghost in about 5 billion years. We're about halfway through the life expectancy of the sun. But the sun will be dead long before that happens. And so I wouldn't worry about it.
Yeah, there you go. So that's the real answer. The real answer is, Danny, you shouldn't care.
Exactly.
It's, it,
But I
it,
want to
it-
be around to watch that rip.
that would be, yes.
Except I would be in the universe that was ripping, and so I would be ripping apart as well. Just
I live every day in a universe that's ripping.
because no, but think about it. When you zoom in on a photo, that only works until you start seeing the pixels
Right,
that comprise the photo.
right.
If you keep zooming in, there's no more information there. But what happens if you keep zooming in and you want to break apart the pixels themselves? What's between them? Who knows? In between the pixels of the photo that you're zooming in on. And so this is the mystery and the uncertainty we have in 22 billion years. I have it on my calendar, by the way. As I say, October 12th, 22 billion years from now.
22 billion years
Watch
from
out.
now. There you go. That's very cool. I believe that's a Wednesday, but
Yeah, thank you.
yeah, yeah.
Chuck the Savant. Yes.
You pick any date 22 billion years from now, I'll tell you what day it's on. All right, this is James Booth, and he says, my question is about dark gravity.
Okay.
I understand it.
Which is what most people would call dark
Dark
matter.
matter.
But he knows I'm calling it dark gravity because that's literally what it is. It is gravity, and we have no idea what's causing it. It's not even black holes, by the way, or unilluminated matter. We have good reason to know that that's the case. But go on.
He says most of the matter we experience that makes up the stars of galaxy only makes up about 5% of the content of the universe.
Correct.
Okay. If that's the case, which you just said it is it possible that, given we interact with such a small percentage of the universe, we are indeed the anomaly? This really makes me feel weird.
Yes, yes. So it's imagine you're at night and there's an ocean in front of you, but you don't really know it. And you turn on your light and you see these white caps, okay, which show up nicely under moonlight. And we are the white caps of an ocean that surrounds us. So, correct. We are if there were beings made of dark matter, dark energy, they would see us as a contaminant in their universe.
Oh,
That's
look
right.
at that.
Yeah, I know. I know.
Wow.
It's sad.
Well, yeah, it
Yeah.
is. I mean, but
We are
it makes
not
sense.
representative of the most common stuff in the universe, which, by the way, is a violation of the Copernican principle. Copernican principle says that we are not special in time or in place or in location. We're orbiting an average star in an average galaxy. So statistically, it says that we're average, but if we are contained within that 5% of all the laws of physics, chemistry, biology, and all the ingredients that make up matter as we know it, then we are something unusual in the universe.
But could we be the average inside of the unusual?
Yes, we are. Yeah, yeah. So I was going to complete the thought and say, given that we are unusual, we are average.
There you go.
Okay, there you go.
Very nice. Very nice.
You know, another example of that is, you know how the school systems try to corral all the smart people together, right? Well, they used to do this. They put the smart people
No, they
in
do
their
it
own
still.
class.
They
Okay.
have all the AP kids are in the AP
Exactly,
class.
exactly. So in the general population, you're unusual because you're like smarter than everybody else. Then they put you in the AP class, and now you're
Just average.
just average. You see,
Everybody's
that's how that
smart.
works.
That's right. That's it. A problem I did not have.
Therefore, that little bit of math was something you didn't have to think about. Is
Did
that what
not
you're
have to
saying?
worry about that.
No, I remember. Okay, so I was not in the smart class in elementary school, but I was in the next class because they totally ranked these classes, and I remembered the kids in the smart class. They got to take French. I'm talking about sixth grade, my elementary school, before there was middle schools that would absorb a sixth grade class. They took French. They had a French person, and I said, they're learning a foreign language.
And learning how to smoke.
With the hand in front of
Bunch
the
of fourth graders sitting around. You speak my language, and it sounds like how you say a dog pissing in my ear. I don't know why, but you bore me.
Why does every French person you imitate smoke a cigarette? Why?
It's just worse.
What they were deciding what you would learn without me saying I want to learn it, and we're not measuring my ambitions for what I could or could be in life. And this is, for me, that's a travesty. Who have we lost in the educational system for want of an educational program to identify where the ambitious kids actually are
Right.
versus
Oh,
those who scored high on a test?
and more importantly, not just the ambitious kids, but what are identifying their ambitions. Because if
Exactly.
you identify an ambition, you automatically excite the person to learn
Exactly.
because they're pursuing what they already like.
Exactly.
Yes. Awesome.
Chuck for president. Okay. You got it.
All right,
All right,
here we
next
go.
one.
This is, let's go to uh, Rotten Josh, aka Transmetal 2. Hey guys, this is Rotten Josh here from Somerville, Florida. My question: instead of the Big Bang, could the universe have formed from a big implosion instead of an outwards explosion? When I think of the Big Bang, I imagine exploding outwards. So I was thinking maybe it exploded inwards. And thank you for your time.
Before we had good data on the very distant future history of the universe,
Right?
there was our equations that are traceable to Einstein and others, including what's that dude's name? He was a Belgian priest, actually, who contributed mightily to our understanding of the Big Bang. And he, so but anyhow, so it under the Einstein's equations, it can sustain a collapsing universe as well as an expanding universe. So people naturally said, if we measure an expanding universe, maybe it'll one day recollapse and then start all over
Start
again.
all over. Okay.
Yeah, and that's why you get this sort of these rhythms. By the way, the name of that Belgian priest is Georges Lemaitre. Georges Lemaitre.
Georges
Yeah.
Lemaitre.
Lemaitre. Yeah,
Yeah.
yeah. And so he took Einstein's equations and said, wait a minute, this can give us an expanding universe. And if we're expanding, that means it had a beginning. If it had a beginning, that's interesting. And then a lot of religious people said, oh, a Catholic priest says that, in fact, there was a beginning, because before then, no one knew how to think of a beginning of the universe. It was not a thought. It's not that they thought about it and said there wasn't. It's like, of course, the universe was always here.
Right.
How could everything that there is have a beginning? So we have Einstein's equations. Georges Lemaitre says there's a beginning, and then everyone is jumping on that, saying, see, Genesis is true. God's made the beginning. And so he said, no, this ain't got nothing to do with Genesis. Okay? There was a little spat between the religious folks who were reaching for this scientific result and the Catholic priest who came up with the result, who was in denial of it confirming biblical Genesis. That's all.
Oh wow. Look at and he was Catholic.
And he was
That's not
Catholic.
that's kind of rough when your
Yeah.
own people are just like, nah. That's it's kind of like you appoint a special counsel and he goes, yeah, there was no fraud in this election, and you go, yeah, you're fired.
So anyhow, so in that scenario, until you have data to show which version of these, what variant on this equation is operating, you could have a cycling universe. And this is how old I am. When I was in graduate school, we explored all of these solutions to the equation. But we know now from data that we're on a one-way trip. The universe will never recollapse. So no, we're not going to have a collapsing universe. And the birth of the universe, could it have been a universe before that collapsed and then birthed us again? We don't know.
Oh, okay. Well, there
It
you
would
go,
be
buddy.
hard to have a collapsing system expand and then never recollapse.
Right.
You see what I'm saying? So, because whatever made it collapse should make it collapse again, and there's nothing out there that's going to make that happen. So,
Interesting. There you go.
there you
All
go.
right. Hey,
Yeah.
nice question, man.
Yeah.
Way to go. So this is Gaud Haraginadoni, or Haraginadani says this. I'm from San Jose, California. My question regarding shyness of dark matter when interacting with other matter. If we think dark matter as a giant spiderweb that holds the Earth and the sun and the gravity, why does it interact with dark matter that holds the Earth and the moon together? Or the dark matter that holds our solar system and the Milky Way in the galaxy? With normal matter, these three spiderwebs would scrape and break each other. Dark matter is pretty outgoing all over the place, holding galaxies together and whatnot. But when it comes to interacting with other dark matter, why is it so bashful? Is it because it's afraid of rejection? Or maybe it's just not interested in a three-way, or whatever reason? I'm just curious. Please let me know. I think he was trying to do a bit at the end there. I'm pretty sure he was trying to get a little bit at the end. But I read it anyway just to satisfy you. You got your little comedy bit in there, Gal. But yeah, is there different dark matter that's doing different things?
Yeah.
In
So
different
dark
parts
matter
of the
is not holding Earth together.
right.
The molecular forces are, the electromagnetic attraction forces are. Dark matter is not holding the solar system together. All the objects there is sufficient gravity to make that happen. But dark matter is holding together the galaxy, and it's holding together galaxy clusters. So it turns out, other than through gravity, we don't interact with dark matter. So you could just walk through dark matter, you wouldn't know it, and it wouldn't know it. More accurately said, you wouldn't know it, and it wouldn't care. Okay? So now, not only do you not interact with dark matter does not interact with itself.
Ooh.
Because if it did, you would have concentrations of dark matter. Just think about it. If you have two hot marshmallows and they meet at night, okay, over the fire,
Right.
what'll they do?
Well, they'll get it on because they're both hot. So, I mean, that sounds like a recipe for marshmallow love if I ever heard it. Two hot marshmallows coming together.
That was not my intent for you to take it down that path. So, two hot marshmallows, they'll stick.
They'll stick to each other.
Okay? So
Right.
there are forces within the marshmallow, material forces, that when it sees other marshmallows, that they'll stick. Okay? So our matter knows how to do this. All right? That's how you get planets. That's how
Right.
you get stars.
Right.
Dark matter does not stick to us, so it's not with the marshmallow or with the planet or with the star, and it doesn't stick to itself. So dark matter does not make concentrations. So as far as we know and understand the behavior of dark matter, you don't expect to see dark matter planets or
Right.
dark matter galaxies.
Dark matter is the Unabomber. It's just lone. It's a lone wolf.
It's
Out
lone
there by itself.
by
and
itself.
it does not care.
Okay, there it is. Unabomber, that's a stretch, I think, but
Yeah,
okay.
he was kind of a hermit, right? He didn't care about anybody. I mean, listen, I don't know.
There's a morbid stretch, I might add.
It was
but
a morbid stretch.
But anyhow, so yeah, it's just the interesting part is that it doesn't even interact with itself physically, only through the force of gravity.
Nice.
So
All right.
watch, you have a forming solar system, and two bits of matter know this, and they fall towards each other and stick. All right.
Right. Right.
Now watch, you have bits of dark matter, all right, and they fall towards each other, and they pass through each
Pass
other.
through each other.
Right, and
Right.
and they'll just rock.
Very
There it is.
rude. Very
Right.
rude.
Very. There you have it.
Oh, very cool. Well, that's a great question, man.
All right,
Okay.
keep going. We're getting through these, Chuck.
We're getting through them. People have made note that sometimes we take and luxuriate in our question answers, but
Yeah, no, we're making
uh,
progress here.
Yep. So this is Bob Dan. And Bobden says this. Hi, this is Bob is from the US of A. If space in the universe is expanding, then why aren't we being stretched thin and ripped apart atom by atom? And what am I missing here? I mean, wouldn't the expansion apply at every level? Right down to the subatomic? And how is this current expansion different from the so-called big rip you talk about? And here's what I want to know, Bob Dan. Why do you have such a damn attitude?
You gave him the attitude.
I'm just reading it the way it's written.
No, you are imbuing This boy's question with attitude.
Okay. I mean, it's just I don't know the way it sounds that he's
I
that
could have read
maybe.
it peacefully and calmly, I'm sure. Okay.
Okay, that's true.
So the expansion of the universe, depending on the rate and where it's happening, it will not overcome the gravitational forces that are and the electromagnetic forces that are otherwise binding solar systems and objects together. The expansion of the universe has to be way stronger
Right.
before that happens. So, in other words, yes, you're stretching space, but I'm holding on to myself within the stretching space until the force of the stretching space exceeds that of my gravity or exceeds that of the electromagnetic force. Then it'll pull you apart.
So the fundamental forces of the universe right now are greater than the ripping forces that are enacted upon it.
Correct. Correct.
Boom.
So
Got
you got it. So the gravity, if you got a tight gravity system, it's you're not pulling that apart with your expanding universe yet.
cool.
Yeah.
Very cool. Well, I'm sorry for giving you so much attitude when, when I read the question. It's a good question,
Wait,
man.
give me what sentence had the most attitude there? Read it to me.
Okay, okay. And how is this current expansion different from the so-called Big Rip?
Okay, so I would read that. Oh, and how is this current expansion different from the so-called Big Rip? See?
That's why you're an astrophysicist, and I have problems with my my phone carrier.
What? Okay. All right, next question. What do you have?
I'm just saying, I get on the phone with them, and they're just like, "Sir, you cannot talk to me that way, and I will not have you
Click.
talk."
Right, they can hang up on your
They
ass.
can hang up on you now.
You've used profanity, they'll just hang
They
up.
can hang up on you now. Then and it's totally fine.
Hmm.
I don't ever use
You know the
profanity.
question is, if it's AI, had you have the conversation, will the AI hang up on you,
See,
or will
that's
it
funny,
cuss you back?
and that's what I'll say from now on. I was just trying to figure out if you were AI. Don't hang up. Don't hang up. Just wanted to make sure you weren't AI. um, anyway, this is Michael Rivera. Michael Rivera says, "Hello, Dr. Tyson and Lord Nice. Michael here from Las Vegas. My question is, would it be possible for humans to artificially create a black hole with significant mass in order to further study the mysteries of how black holes work and what they do? If so, how dangerous would this be, this artificial black hole made here on Earth at a sustainable size? And would there be any way of containing it?" This guy, Michael, I have a feeling, is trying to make a black hole in his basement or something.
These basement people, I worry
Yeah,
about them.
he's
See, I grew up
scary.
in an apartment. We don't have any basement projects, hidden from the parents.
That's funny. Neil, don't make me come in there. I feel like I hear a black hole being built. What's going on?
What would that sound like? So, um, yeah, you wouldn't know how to contain a black hole. It's like, Chuck, pass me that black hole. Chuck, where'd you go?
That's funny. Chuck. Chuck?
Neil.
Oh, that's funny.
So yeah, so you can't we don't know how to manipulate a black hole,
Right.
and so maybe someday we could like bunch up space time and make a little container out of I don't know I don't know. So yeah, this would be a really bad idea because a black hole is a voracious eater. So let's say you had a black hole on your desk and it fell to the floor,
Right.
it would start eating Earth. And it would just fall through Earth, eating any part of Earth that was near it. And it would continue to do this until the entire Earth was inside the black hole. And you know how big an Earth mass black hole is?
No.
About the size of a plum.
Oh, wow, that's crazy.
That's a sad day for Earth.
That's a
So
sad day.
so yeah, so your black hole eating Earth would become the size of a plum.
Wow.
That's the entire Earth fitting
That's the
inside the
entire
black
Earth
hole.
inside the black hole.
Yeah,
Right. Yeah.
yeah,
Look at that. Oh man, that's so cool. Like
yeah. It's scary
all
too.
of
Yeah,
Earth crunched down into a something smaller than the size of my fist.
yeah.
That's it's very difficult to really conceive when you think about
Yeah,
it.
because you're limited to your 5 biological senses. And the
Exactly.
universe is, repeat with me, under no obligation to make
Mm,
sense to you.
there you go. And guess what? It does a very good job of that.
Okay.
It's winning in that battle as far as
Hmm.
I'm concerned. All right, this is Captain James Riley. And Captain James Riley
We know
does not
we gotten a lot of his questions.
yeah,
Captain Riley.
Captain Riley.
Yeah.
Yeah. He says, why do galaxies form a web or a sponge shaped structure? It seems that on small scales, gravity forms spheres and disks. So I'm a little confused.
Oh, oh, good question. Right, the large scale structure of the universe is not with galaxies equally spread. It's not with galaxies all in tidy spheres, although some galaxy clusters are. For example, the Coma Cluster of galaxies. This is a cluster of galaxies that lines up with the stars in the constellation called Coma. Okay, a Coma Berenices, so it's the hair of Bernice. Okay,
Ah,
so yeah, if you look at on constellation maps from like
right.
centuries ago when they used to draw this stuff, it's just somebody's hair. It's
Right. So, yeah, not to be confused with the comb over galaxy,
no.
commonly seen in boardrooms around America.
Come over.
The comb over galaxy.
Okay, so the Coma Cluster, that's a nicely spherical cluster of galaxies. And in fact, that's the first galaxy cluster where dark matter was discovered. Because you looked at all the speeds and there's a certain amount of mass, gravity required to keep all of them in this ball. Whole galaxies now, thousands of galaxies. I think like maybe 800. I forgot the exact number, but it's around 1,000 galaxies. And many hundreds. And so you calculate that up and you find out that it needs like 10 times that much mass to keep the galaxies contained. If you add up the mass of every galaxy, it doesn't add up to the gravity needed to contain them. So that was a guy named Fritz Zwicky in the 1930s, 1936, I think it was, where he's a Caltech, Swiss-born Caltech astrophysicist who discovered this. It's the longest unsolved problem in modern astrophysics, the dark matter problem, birthed with his observations. Anyhow, there are some galaxy clusters that are nice spherically shaped. Others, you see these filaments. It's as though you had a sponge and you cut it and you looked at the cross section where there's some concentrations of sponge, but mostly there are these sort of bridges between concentrations. That's what the universe looks like, the inside cross section of a sponge. Here's the problem.
Mhm.
If you look at how fast the galaxy is moving along one filament and look at the size of the filament, the universe is not old enough for the galaxy to have crossed that filament.
Ah,
So you don't have structures that represent what the galaxies really want to do if they had enough time.
right.
So that's what's going on here,
Interesting.
right? So you have systems that are not gravitationally settled in what they should look. The Coma Cluster is, all right, and it's a term we use for this. I forgot it. What is it? It's a relaxed cluster is one where okay, we got this. Everybody's orbiting just the way they should,
Take a
and
chill, baby. Take
with
a
this chill.
chill.
That's exactly. And they could cross the size of the cluster in the time the universe has been around. So that how you know everybody's settled into their routines. Any structures bigger than that, they have not had time to settle. And they may never settle, given how long it takes and given how fast the galaxies are moving through space. So yeah, that's how and why we get that.
Wow. Very cool. Lou Perot says this. Hi,
Perrault, is
Neil.
that
Hi,
a
Chuck.
silent T or are you
AULT.
oh Perrault. Okay. Okay.
Peralt.
Yes.
Okay,
Uh-huh.
Lou Peralt. He says, hi, Neil. Hi, Chuck. My name is Lou, and I'm writing from the Seven Islands, Septiles. He says, in
Where are
Quebec.
those islands?
In Quebec. My question is it possible to see past by looking see the past by looking into deep space? And if so, which direction do we have to look? And also, is it possible to see the Earth by sending a telescope multiple light years away?
Yeah. So only if you can travel faster than light can you see your own past. So you can't do that. But so I know what he's saying, but I want to lead up to that. So clearly he knows that the farther out you look, the farther back in time you see.
Right.
Okay? So there are galaxies that are like 65 million light years away from Earth. Okay? From our galaxy.
Wow.
So right now, if they had a super duper telescope and they look towards Earth, what do they see?
If they're seeing us however many light years ago.
65 million years ago.
Right.
What are they witnessing?
Dinosaurs, right? Oh, and they're getting killed.
Thank you. Okay.
It just dawned on me what that time frame was.
There
I'm like,
you go.
oh, snap.
I know.
The Earth is
So,
putting on a show for them.
yeah, so the galaxy that's 65 million light years away is witnessing the extinction of the dinosaurs because that light is only now just reaching them.
Right.
Okay. So, but we can't see our own past. That doesn't work. So, yeah, but if you send a telescope out there, let's say 1,000 light years away, and then come back, it will be seeing whatever happened here 1,000 years ago.
Right.
Right.
Yeah.
That's all. It's that simple.
So yeah, that's it. So and then what you'd have to be, like you say, is faster than the speed of light, so that you could go place it and come back and have it and be like, "Yo, what's up?
Yeah. Wait.
Yo, what's up? What's up? It's me."
Yeah.
All right.
So once you go fast as speed of light, then all bets are off, and then you can do all kinds of paradoxical things.
Cool.
Yeah. Mm-hmm.
All right. This is Connor Home. He says, "Hi, if the Big Rip does occur." A lot of Big Rip questions today. People got it on their mind, man.
Because no one wants to be
Torn asunder by the universe itself.
no one wants a new one torn into them. Okay?
Yes. Yeah. I'm the universe, boy. I will tear you a new one. That's what I will do. You keep it. You say another word. Say another word. I dare you. Watch what I do. I'm the universe. You know who you're talking to? I will tear you a new one. Connor says, if the Big Rip does occur, what would be the immediate results of tearing of the fabric of space-time? Would these tears be black holes, or would they simply just be voids of nothingness? What is nothing? How could nothing come out of something? What would these voids be? Wow, that's freaking crazy.
Okay.
I love this, Connor.
Okay, so my simple answer is we have no idea.
Oh.
Okay, the state of the universe post Big Rip is a complete mystery. And what we don't know is there some law of physics that will manifest at that time. Think about that. When do we discover new laws of physics? When we step where we had never previously stepped. When we look where we never previously looked. When we bring a new kind of apparatus, a new kind of detector that we never had before. Then we see the universe behaving in ways we've never seen before. Sends us back to the drawing board to say, is this understandable with previously known physics? Or do we have to invent new physics? So,
Right.
Einstein said to himself, I don't think we'll ever have a black hole, even though his own damn equations predicted it, because a black hole in his equations have infinite density, occupying zero volume in the center of the black hole. And he said, surely there's some new law of physics that's going to show up and save us from ourselves, save us from this mathematical craziness where God divides by zero.
Right.
So, what happens in the Big Rip? What would it look like? We do not know. And I'd like to know before that day happens so that we can protect ourselves, if that's possible at all. We don't know. And he's wondering if it rips, does nothing show up? Okay? Something we call nothing.
Something we call nothing.
Okay, but then what is nothing?
What is?
Okay? I think we have a whole explainer on nothing.
We did
don't we?
do an explainer on
Okay,
that.
let me tap some of that.
What we got out of that was there is no nothing.
Because is air nothing? Well, you can see through it, but we know there's air there, right? So clearly it's not nothing. So now take away the air. So what's left? Is that nothing? Well, it's still space.
Right.
Well, it's empty space. Nothing. And we know from quantum physics that empty space is a seething soup of what we call virtual particles popping in and out of existence. And and this is what we call the vacuum energy. You just Google that, vacuum
Yes.
energy. There's an energy in the vacuum of space that quantum physics puts there. And we thought, hey, that could be the dark energy in the vacuum of space. So you do the calculation for how much dark energy we measure, then you do the calculation for how much pressure is coming in from these virtual particles popping in and out of existence, and we are off by 100 orders of magnitude. It is the biggest mismatch between an observation and a theory that has ever occurred. This is further evidence that we have no clue what dark energy is. Okay.
Wow.
So there it is now. And could we imagine a place where there's not even these virtual particles? Okay, but then you can't have quantum physics. So, all right, so now we have a place where there's not only not nothing, there's not even the laws of physics.
Right.
Whoa. So could you exist in that nothing?
Yeah.
Because you only exist because they're like molecules hold you together, and and light and energy and you only exist because the laws of
The
physics
something.
allow you to.
Right.
So the best nothing, if the rip gets you there, if you step through that rip, maybe that nothing does not even contain the fabric of empty space.
Look at that.
Because the laws of physics tell us what the fabric of empty space does. So if you take away not only the empty space, but the laws of physics that would describe it, then that's as good a nothing as I can imagine.
Right. And that nothing exists inside of a bong. I've been there.
You've been here.
Been there. Tell you.
The bong nothing.
It's
Okay.
a bong nothing. It's a nothing bong.
So, Chuck, we have a couple minutes left. I think I'm going to allow you to give me one question, even though you're a cheap ass comedian not paying your Patreon dues.
I was watching this listening to NPR, and they were doing this thing about energy and all the different forms of energy. And then they, for some reason, played a clip from what I know is one of your and my favorite movies, The Matrix. And they played the clip about how the AI basically, after a singularity, saw us as a form of energy to be used as little batteries. So my question to you is, do we put out enough energy that if something were an AI would say, you know what, I need to put them to work.
And line us up head to toe.
And that's right. Line us in, right. So that we would become little batteries, as opposed to just taking us and literally putting us to work by subjugating us all and making us do their will.
Right. Yeah, I'm just trying to think. If they put you and me in a battery socket, I say, no, Chuck, we got to be head to toe, right?
Exactly. You see the AI keep coming around and flipping us over, flipping us back.
I put it in the wrong way.
Now, doesn't this go on the spring side? The feet go on the spring side, right?
Is that what AI sounds like? That's an exasperated AI.
Exactly. That's my AI that sounds like Chris Tucker. Say, man, doesn't the feet go on the spring side? Okay, anyway.
All right, so this energy described in the Matrix, is drawn from the human body. So you can look at our metabolism. All right. If you're a calorie counter, you'll know that there's something called your basal metabolism. So this is the energy you burn, pay or play. Okay. Just for existing.
Just for existing.
Right. And for some people, it's maybe 1,500 calories a day. For me, it's more like I'm bigger. So for average, I'm a little bigger than average. So like 2,000 calories a day is my basal average. Okay. So now, do you realize that the food calorie is written with a capital C? You might not have noticed that.
Yes.
There's a reason for that. Because a physics calorie is written with a lowercase c. Because a food calorie, one food calorie, equals 1,000 physics calories.
Oh, okay.
So when I say I burn 2,000 calories a day, it's 2,000 food calories. It's 2 million physics calories. And what is a physics calorie? It's the amount of energy required to raise the temperature of 1 cubic centimeter of water 1 degree Celsius.
Interesting.
That is 1 calorie.
That's 1 calorie.
Okay? All right. So, once you have all these calories, it's a rate at which you're burning energy. We have a unit of measure for that. It's called watts. Okay? Watts. And so, when you do the math on this, the average person is operating anywhere between 50 and 100 watts.
Okay.
Okay? So, it's like a light bulb, like an 80-watt light bulb. Okay? There's that 80-watt bulb consumes energy at a rate. So do we. We radiate that. Okay? Or we consume that much energy, our circulation and everything else. So what the machines did, the computers did in the Matrix is line us all up and draw the 80 watts of power from every person at all times.
Okay. That's very inefficient.
So the answer is yes, that's how they did the movie. However, it's extremely inefficient.
Yeah.
You know why?
Because I don't want to power a city off of light bulbs.
No. If you get enough of us, I use light bulb as an example of something that uses that much. Okay. So no, here's why it's inefficient. You're burning 2,000 calories a day, as long as what is happening?
As long as I'm living and breathing.
No. Yeah. Well, yes, but
Well, yeah.
more fundamental than that. Well, equally as fundamental as that. How long can you keep burning 2,000 calories a day?
I thought you said that was my base.
Yes, that's your base.
I got to be eating something.
Thank you. Thank you. Thank you. Where do you think
eat
that
something to burn them?
Where do you think those calories came from? The food you're eating. So, in order for all of the Matrix people, the people in the pods, to be feeding 80 watts of power to the Matrix has to feed them.
Ooh, that's 8 billion mouths.
Okay, so what I'm saying is, if the
lot.
Matrix is feeding you
Right.
2,000 calories a day so that it can then pull your 80 watts off of you, why use the middleman?
Right.
Just burn the food calories that you're feeding the people. In fact, every time energy changes from one form to another, it's not 100% efficient. You lose some energy to heat. All the time.
Right.
So you look at the energy in a gallon of gasoline, okay? And that gets burned to drive the car. I forgot the number. 80% of that energy goes into heat. It does not go into moving your car forward.
That's funny.
Okay? So this is a fundamental feature of thermodynamics in the universe. So they were being inefficient. So this is their weak point in their storytelling. And I will give them a hall pass because they did everything else so brilliantly. But that one was just plain stupid. Because the machines, the computers just would have used the food that they're feeding them and get their energy off of that and leave the people out of it.
Look at that.
But then they wouldn't have had a movie.
Well, that's a problem. Yeah, that makes things difficult, Dustin.
Yeah, that they wouldn't have had a movie. Then there's no
All
movie.
right. All
So
right.
there you go. Yeah.
Cool.
All right. That's all the time we have, Chuck.
Okay. That was
All
fun.
right. So what was it? This was
Cosmological Curiosity.
Cosmic Queries, Cosmological Curiosities. I got it.
Yeah.
I got the tongue twister. All right, Chuck. Always good to have you here.
Always a pleasure.
All right. This has been StarTalk, Cosmic Queries, Cosmology Edition. Neil deGrasse Tyson here. As always, keep looking up.